So keeping with the theme of theory we've been kind of transitioning to in this class, we're going to move on to this topic that you've heard me kind of name drop throughout the entirety of this course, and that is this notion of a basis and basis vectors and things of that nature. And this, now that we're kind of a little bit more familiar with vector spaces, and we have ideas that vector spaces are just these planets that contain vectors, and we care to call them vector spaces and verify that they are vector spaces so that we can do math with them. We want to make sure that when we're adding vectors together in the space that we don't end up outside of the space, that basically like we just have a fixed set of rules that we've agreed upon that are like, yeah, these are good rules to have, and if we have them and we can follow them, then we can do some meaningful math. And so this idea of what a basis is really focuses on two things. It focuses on linear independence and the ability to span a space. And so before I give you the formal definition, the rough idea is, if you recall back in R2, I brought up the notion that we have these what are called standard basis vectors. We had what we called the I hat vector, right? The I hat, which was the standard basis vector 1, 0. And we also had J hat from Calc 3, and this was the standard basis vector 0, 1. And the idea, what I had said before, if you had caught it in the previous videos, was that these vectors are pretty cool because I can use them to basically construct any other vector in the space, right? If I want to create the vector for 3, then all I need to do to create this is take 4 of I hat and add it to 3 of j hat, or in other words, just do 4 times the vector 1, 0, and then add it to 3 times the vector 0, 1, and that's going to, of course, get me the vector 4, 3. And it turned out that, the standard basis vectors, we usually call these, and we stop assigning them letters after a while. We call this one E1, we call this one E2, and so on and so forth. But it turns out that, it doesn't just have to be 1, 0, and 0, 1. The idea behind a basis is that you can create building blocks for the space out of anything. There's just a couple of rules that we need to follow. So I'm going to give you a definition. And the definition for what a basis is fairly straightforward. So we're going to say, we're going to be working with some vector space. So we're going to say let V be a vector space. Okay, so we need our vector space. That's where we're going to be doing our math. And then we're going to say a set of vectors. We're going to say that set, we're going to call it B, right? So that set B, which we're going to say it's a subset of the vector space V. So basically just that these vectors exist in V. That set is a basis, what we call a basis, if the following two things are satisfied. So number one, B is a linearly independent set. Linearly independent set. And the second criteria is that basically that we can get V if we span the vectors that are inside of B, right? So if we span B. And that should kind of, ring some bells, right? The idea being that, look, if I consider all possible linear combinations of 0, 1, and 1, 0, I will be able to get all of R2, right? Because in general, when we talk about this for R2, what we're talking about is we're looking at x1 times 1, 0 plus x2 times 0, 1. And we're at, this is supposed to, does this span R2 means that this thing needs to have a solution, or rather that the matrix equation AX equals B needs to have a solution for every single input X that we could come up with, and that X, of course, relating to these coefficients. And it does, right? We can show this by doing row reduction very easily, although, in fact, we are just if I pop this as a matrix equation, I just get 1, 0, 0, 1, and B1, B2 very quickly. And I can solve this and immediately tell you that my x1 is B1, my x1's B1, and my x2 is B2 every single time, and voila, we have spanned. And then the fact that these are linearly independent is pretty straightforward. The fact that we have 2 pivots in a 2 by 2 matrix means we have no free variables, thus linearly independent. And so, why do we care about basis vectors? In the next video, we're going to really kind of dive into this idea, but just as kind of like a glimmer of, of hope for yourselves to kind of hold on to, the idea is that sometimes, while the standard basis is very nice to work with because we've just used it a lot, it's not always necessary that we use just I hat and j hat to talk about R2, right? Maybe I give you the vector 3, 4, 3, 4, and I give you another vector, and this is the vector, 7, 2, right? Not drawn to scale. And my question for you is, do these 2 vectors span R2, right? Do these span R2? And it turns out that these ones do, because you can kind of reason it to yourself. They're since there's only 2 of them, we just have to check and make sure they're not multiples of each other, which they're not, which means they're linearly independent. And the last thing we have to check is that they span R2. Well, if you have 2 linearly independent vectors, you're going to span R2, so you're pretty much done. But a natural follow-up would be, why would I want to use those vectors over the standard basis vectors? That's a really good question. The short answer is something to just kind of think about is maybe you're working with a picture or some distorted image that is kind of shimmied like this, right? And then we might find that it's actually easier to tessellate this thing or to make copies of it or move it around if we describe it using the vectors that make up kind of the corner edges of this photo, rather than if I use kind of like these awkward ones that maybe kind of do this, right? And so it may be in our best interest to use different vectors as our basis instead of what we call the standard basis vectors. And so that's going to be a theme in the next video, but in this video, we're just going to kind of get the hang of, identifying, what a basis is and what it really means, and kind of going through examples of things that are indeed make up a basis. So, for example, we know the standard bases for R2 and R3, but maybe, for example, so the standard basis, we call the standard basis for, let's see, for P sub n, so for our nth degree polynomial space, is the vectors 1, t squared, t cubed, comma, t to the n. Okay. And you'll notice, why do we need so many? Well, because, and remember that any polynomial that's in this space, or rather any vector v that is in this polynomial space, is of the form that v is equal to, well, let's call it x1. x1, or let's start with x sub n. x sub n t to the n plus x sub n minus 1 t to the n minus 1 plus plus t, or x squared, not x squared, x2t squared plus x1t plus x sub 0, right? And the idea being that we cannot create every single polynomial in this space unless we have one piece coming from each of these items, right? We cannot do it, okay? And so that's the standard basis for P sub n. So that's not too bad. One other thing you may notice, if you're a very astute observer, is how many vectors are in here? How many vectors are in here? How many basis vectors do we need for the nth degree polynomial space? And it turns out that we need n plus 1. In this case, here we need n plus 1 basis vectors. Or rather, I won't even say it. We'll just say we need n plus 1 vectors to form a basis for the nth degree polynomial space. Okay. How many do we need for R3? Right. So example, for R3, right, what's the standard basis look like for R3? Well, the standard basis for R3 is the set of vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Right? So you'll notice that here we only need 3, it turns out. Okay? And it turns out, well, that we have a name for this, and so we say that the dimension of a vector space, the dimension, kind of like the size, it's a way to refer to the size, but the dimension of a vector space is given by what do you think? By the number of building blocks we need to build that space, aka by the number of vectors required to form a basis for that space. Right? So the dimension of R3 kind of is pretty straightforward. It's 3-dimensional. It takes 3 basis vectors. But something that blows people's mind is, like, for instance, if we're talking about P2, which is, the second degree polynomial space, this vector space has dimension 3 because the standard basis here is going to be 1t and t squared, right? I can't get, for instance, if you take out any one of these, right? Let's say you remove the number 1, right? Then how on earth would I construct the polynomial 3t squared minus 7? You couldn't do it. Like, it would be impossible. You need that 1 there. And if you're like, okay, well, can I remove something else? Well, you can't remove t squared because how would you build the polynomial freaking t squared, right? Couldn't do it. And that inherently is kind of like the reason why we like these basis vectors. They're like the minimum number of vectors we need to really get stuff done in a space. And if you remember earlier when we talked about linear transformations, it turns out that when you want to see like what's going on in a space, the reason why we like to talk about the basis vectors for a space is that if you want to know what's going on via linear transformation, you don't have to know what's going on for every single vector in that space. You really just need to focus on like what the heck is going on for your basis vectors, because since your basis vectors make up everything else in the space, if you apply a linear transformation to these and you're like, oh, okay, I can see what's happening to the basis vectors, you immediately are going to know what's going to happen to every single other vector in the space. That's a really nice kind of side result that we get from working with basis vectors. All right, so let me toss kind of another idea down here, and so it's a theorem. It's going to be kind of loosely defined, but if you have an idea of kind of what a basis is in theory, let's let our vector space V be equal to the span of some set of vectors, some collection of vectors, v1, comma, dot, 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 comma, v sub p, okay? So, right, you might be thinking, oh, well, V is spanned by these vectors, therefore this set of vectors is a basis. And the idea is that no, it's not yet, because we could have linear independence and we could have linear dependence in these vectors, okay? And so what the theorem says loosely, and you can read the really technical written out version in the textbook if you want, but the big idea is that if we have a set of vectors that spans a vector space V, then if, this collection of vectors v1 to v sub p are linearly dependent, then we can remove all of the, the linearly dependent vectors until we have a set of just dependent vectors. So we can remove all the linearly dependent vectors until all that remains is a set of linearly dependent vectors And as soon as that happens, that set, it will still span, span our vector space V, and thus now be a basis, right? So let me make one. Let's make something up, right? So what if I ask you, to take the set. So consider the set 1, 2, 3, 4, and 5, 6. So let's consider the set of these three vectors. And what I want you to do is I would like you to reduce this this set to a basis for R2. Okay? And R2. Okay. So the idea here, like, we clearly have three vectors, and if we don't know which ones are linearly dependent, which ones are linearly independent, it's a pretty nifty process. We already kind of have the idea of what we should do here. Is that all we're going to do is we're going to pop these into a matrix, and we're going to row reduce this thing. Okay, so we're going to take, we're going to replace row 2, and we're going to take -2 row 1 and add it to row 2. And that's going to give me a new matrix, 1, 3, 5. It's going to give me a 0 here. And then if I multiply the first by -2, I'm going to have a -2 here. I'm going to have -4 here. And then next up, I'm going to just multiply this by, -1/2. So row 2 is now going to be multiplied by -1/2 of the original row 2. That's going to give me 1, 3, 5, 0, 1, 2. And then the last step is going to be, we're going to replace that 3 with a 0. And so we're going to take, we're going to place row 1. We're going to take -3 of row 2 and add it to row 1. And what this is going to do is we're going to get down to 1. We're going to have 0, 1, 2 here. We're going to have a 0 here. And then -3 times 2 is -6, plus 5 is -1. And at this point here, what can we conclude? Well, if we were setting this up and asking, do we have linear independence or dependence, right? One way we could do this is by taking this and setting it up in the form x1 times 1, 2 plus x2 times 3, 4. You may remember from the invertible matrix theorem that if we try and solve this, and we set it equal to the 0 vector, right? According to the invertible matrix theorem, if this thing has a non-trivial solution, basically that x1, x2, x3 all equaling 0 is not the only solution, that means we have linear dependence. And sure enough, right, this should make complete and total sense, because that would mean that I could rewrite this as x1 times 1, 2 plus x2 times 3, 4, 3, 4. And that's going to equal some constant, x3, and yeah, it's negative, but pretend it's a new x3, 5, 6, right? It's going to basically allow us to combine these two and give us the third vector, et voila. So you can imagine that because the fact that when we row reduce this thing into row reduced echelon form, we have this extra little column here, right? You can imagine that if this was an augmented matrix 0, 0 here, that what we just found out is that we're going to have a free variable, right? And so it basically means that this column here is extra, which basically means that this vector right here is extra. And so if I wanted to, reduce this set to a basis, I basically just figured out that the set that consists of the vectors 1, 2 and the vector 3, 4 is going to get the job done, because now I have two vectors for R2. They are linearly independent. They clearly span all of R2 because we only need two pivots, which is what we have, and we're good to go. And so this is how you can take an existing set and create a basis, or check if we indeed have a basis. Let me see here. I guess the two other things that we talk about having a basis are going to be like the null space and the column space, just because they're so common. So when we talk about a basis for the null space, We've already done this before. We just didn't put a name to it. Remember in the process for figuring out like how do we come up with a set of vectors to describe the null space? What we do is we look at how many free variables there are, right? That this is like if we want to talk about how many vectors are going to make up the null space. So look at how many free variables there are. That's going to give you the dimension of the null space, right? Which is what we call the nullity of A. And that's going to tell you how, what those basis vectors are. So, for instance, if you solve, if we're solving the matrix equation AX equals 0, and we get down to the point like what we did earlier, where we get down to the point where we have, x1 is equal to x3 and x2 is equal to negative 2x3, then these things combine to tell us that we could solve this equation, and it's going to look like x3, negative 2x3, and just what? Well, x3, right? Or actually, this is in two-dimensional space, so we're just going to have x3 and negative 2x3 here. And this just gives us x3 and then 1 and negative 2. And this right here is your basis vector for the null space of A, right? So remember, the null space of A is all the vectors in R2 in our domain for this transformation, which is also R2, that will map to the 0 vector in our codomain. And we just found out that this will do it. Any multiple of this vector is going to snap to the 0 vector in our codomain. That's exactly what this is, because we just solved this equation for the example I gave above. We solved that equation, and we figured out, hey, any multiple of this vector, the span of this single vector, is going to give us the null space. And it's naturally a basis because it's a span, and there's only one linearly independent vector, so that's really nice. When it comes to the column space, so for a basis for the column space of A, all we're going to look at is the pivot columns. So, right, small theorem, right? The pivot columns of A form a basis for the column space of A. And again, this should make sense. If we go back to this example up here, where we're looking at this, it turned out that the first column and the second column, which correspond to the vectors 1, 2, and 3, 4, do a great job at identifying what those pivot columns are. They identify what our basis vectors are, our linearly independent vectors. And this last one is not a pivot column, so it's not in there. And, when we're talking about the column space, remember, the column space of A is saying, what space do we get if we span, right? If we take all the 3 vectors and we span them, what space would we get? But because we only have 2 linearly independent vectors, we're only, the span of those 2 vectors would just be R2, and that's clearly identified by the fact that we only have 2 pivot columns. We only have 2 linearly independent columns. And so that tells us what these pivot columns are as well. Okay, so that's going to do it for this video. Just a brief introduction to what a basis is. Again, just connecting more and more concepts that we've talked about that you probably already had an inkling of, that they worked and that they were useful. And so in the next video, hopefully we're going to get a glimpse of basically, why we care to look at the basis and why we might not want to use the standard basis. So if you're ready and you're interested in that, let's go ahead and check it out.